Hi, everybody. I've had a lot of questions about this integral, the integral of x squared arctan of, say, 5x dx. And so I just want to go over how we can solve this and maybe illustrate sort of some ways that you can break up a computation to sort of keep it clean and make sure that you're able to keep track of mistakes along the way and sort of not run into too big of issues. So let's go ahead and try that. So whenever I see a problem like this, when I have this 5x inside of here, and I sort of, maybe I know what to do. So this one I look at it, and if I look at some examples, I know I should probably try to do this by integration by parts, integration by parts. But because I have this 5x here, I know sort of, well, I'm going to get a bunch of 5s showing up everywhere. And so the first thing I want to do just to keep my work clean is get rid of this 5 sort of once and for all, and then just reintroduce it later. So I'm actually going to start off with a substitution to get rid of it. So I'm going to set y is equal to 5x. So then dy is 5dx. And with that substitution, this becomes the integral of y over 5. So x is y over 5 squared, arctan of y, then 1/5 dy. Good, so I can pull out all those 1/5s, and I end up in front of here with 1 over 5 cubed times the integral of y squared arctangent of y dy. Okay, and now this constant, these 5s sort of sitting here, I have to remember them when I do my final answer, but I can just save that for the very end. Okay, so now I'm going to sort of take this integral. Let me try and do that. So this integral of y squared arctangent y dy. Now you see, I just literally took this and I rewrote it up here. This is something that can be really helpful when you're working on these long problems, is when you start some sub part of the computation, just to rewrite from the beginning. Don't try and sort of make any simplifications when you rewrite it here. I'm just sort of organizing it here. So I'll sort of, here I worked out one part of the problem. Here I'm going to work out sort of the next part of the problem, and so on. It's helpful to keep this organized in different spots on the paper. For example, if I get the wrong answer, if I want to go back and check my different spots, I can sort of break it up into different chunks I'm checking. Okay, so I'm going to do this integral now, and here I want to sort of get the derivative of arctangent, because that's sort of something a little nicer. It just has 1 over 1 plus y squared. So I'm going to do integration by parts to get that. So in this case, I'll set u is going to be arctangent of y. Du is 1 over 1 plus y squared. And then I'll set dv to be this y squared. And then v is 1/3 y cubed. Okay, so now this becomes, when I do integration by parts, I get 1/3 y cubed arctangent of y. So that's the u times v, minus the integral of, so actually let me put this 1/3 sort of all the way up front, because this 1/3 gets multiplied by everything, minus the integral of y cubed over 1 plus y squared dy. Okay, so now, again, that's sort of one chunk of it. I did this part. And the next thing I have to do is sort of this chunk over here. So I have to do this last integral I'm ending up with of y cubed over 1 plus y squared dy. So let me sort of pull that. Maybe I'll sort of do that one over here. It's sort of helpful to draw these arrows so you know sort of where you went. So here, I'm doing the integral of y cubed over 1 plus y squared dy. Okay, and so, well, I want to get this into some form where I know how to integrate it. When you see ones like this, the trick is you always have to sort of reduce the power. If I'm trying to integrate a fraction like this, I need to sort of reduce the power up top. So here I can use y cubed. I can sort of write y cubed in this funny way. So I can write y cubed is equal to, well, that's 1 plus y squared times y minus y. Okay, so why did I do this? Well, the point is 1 plus y squared is sort of what's in the denominator, so I can use this to get some cancellation. So this integral becomes the integral of 1 plus y squared times y minus y over 1 plus y squared dy. Okay, and I'm just going to break this up into two parts. So I just separate the numerator. So this is 1 plus y squared times y over 1 plus y squared plus integral of minus y over 1 plus y squared. So let me pull that minus sign out and just write that as minus integral of y times 1 plus y squared. Good, and times dy, sorry. And now each of these I can integrate. So y, well, the key one on this left one, and sort of the main reason I did this substitution was now like this 1 plus y squared in the numerator and denominator here will cancel. So this first term is just the integration of y dy, integral of y dy. Then I'm subtracting off this integral of y over 1 plus y squared dy. So you might be able to just eyeball sort of what the integral of y over 1 plus y squared dy is, using the fact that sort of the derivative of y squared is 2y dy. Let me just actually just do this with a substitution. So let me do this one over here. So for this integral I have to do, let me set, so I'm computing the integral of y over 1 plus y squared dy. Let me write out, so w is going to be 1 plus y squared, and then dw is 2y dy. So this becomes 1/2 times the integral of w, 1/2 times the integral of dw over 1 plus w. Okay, well, that integral I know how to do, so this is 1/2 ln of 1 plus absolute value of 1 plus w. Good. And then if I sort of substitute back in, so well, what was w? W was 1 plus y squared. Sorry. There's no 1 plus w here. It's just w. So it's 1/2 ln of absolute value of w is 1/2 of ln plus c, 1 plus y squared. I dropped the absolute value signs and just wrote parentheses down here because 1 plus y squared is always positive. You could keep the absolute value signs if you want, that's fine. Okay, good. So I got this part. Now I sort of take this part, and so now I have to unwind everything I did. So I got 1/2 ln of 1 plus y squared for this part. So let me sort of take that over here. Put it on this one. So in the end, for the integral of y cubed over 1 plus y squared, well, the integral of y is 1/2 y squared. And the integral of this guy was 1/2 ln of 1 plus y squared. So let me just write 1/2 y minus, so 1/2 of y squared minus ln of 1 plus y squared. Okay, so that's what I got for this guy. Now, remember this sort of came up here. So I like to use sort of my different highlighter colors so I don't lose track. So when I'm doing this back substitution, by the way, if you could do this on a tablet, it's super convenient because you can sort of do things like this. So I want to take this guy and put it up here. So all told, I get For this integral, I was getting 1/3 times y cubed arctangent of y minus, then what did I supposed to copy? 1/2 y squared minus ln of 1 plus y squared. Good. So I've got this part. And then I finally finish by taking this in. So let me sort of use my other highlight color. So this thing sort of came from over here. And so I need to just substitute in what my y was. So, and bring this constant along. So in the end, I get 1/5/3. So I have this constant still times 1/3, then y cubed. So let me just sort of substitute everywhere y. So y cubed was 5x cubed arctan. So y was 5x, so arctan of 5x minus 1/2 5x squared minus ln of 1 plus 5x squared. Okay, and then of course I still have my plus c, which I sort of forgot to carry along some of the way, but I got it here, plus c. And so this is the answer. Okay, and so you can, by the way, I just want to point out, you can put this in web work just like this. Of course, you could simplify, like you could sort of like take this 5 cubed and cancel with this 5 cubed. You could take like this 5 squared and sort of cancel with this 5 squared. I mean, there's things you can do to simplify this, but you don't need to do that. You don't need to sort of expand out all the constants or like sort of cancel this minus sign with like this minus sign. You can just sort of include these parentheses. So somehow actually you can simplify this further, but if you just input it like this into web work, it will accept this answer, assuming I didn't make any mistakes along the way. But if I did make mistakes along the way, it's not so hard to check what I did because I sort of broke it up into these nice chunks. So first I made this substitution to get rid of this 5. Then I did this integration by parts to get sort of down here. I had this integral, I knew it was going to be a little bit of work, so I sort of went down here. First, I sort of wrote out down here how I broke it up into, by sort of rewriting y cubed to get sort of two things where the numerator had lower degree than the denominator. Then I sort of broke off how to do this one into another substitution over here. So I have it broken up into all these little chunks. And so if I make a mistake, if this answer isn't right, when I input it into web work, I can go back and I can check each one of these individual chunks. Whereas if you sort of don't do that, if you sort of just try to go straight through, it gets really messy with the constants. It gets really, it can get really sort of difficult to check. And sometimes it's sort of, if you don't break it up into these chunks, when you go back to check your answer, you oftentimes just have to redo the whole thing because there's sort of no way to figure out where you went wrong. Good. Well, so anyway, I hope seeing this written out carefully is helpful for some of you. And good luck with the rest of the assignment. Thanks.